Hello student, welcome to our course Wave Optics. Today we have lecture number 25 where we will going to discuss in detail about Michelson interferometer. So, today we have lecture number 25 and today our topic is Michelson interferometer. We have started this in the last class, but today we are going to discuss in detail. Michelson So, let us draw the setup once again. This is an instrument, very important instrument, where we have an extended light source like this, and then light is coming in this path, and then here we have something called beam splitter, which split the incident beam into two parts. One is reflected. The angle of this beam splitter is 45 degree with respect to this horizontal line, and then one part will be transmitted and it hits another mirror here. I call it M1, and then it also reflects from this mirror and come back. Here also we have another mirror sitting, we call it M2. This is M2 mirror, and then it goes up, but here you may remember that we put a similar structure, a glass block with the same material of this beam splitter with the same having the same width. So, this is a beam splitter which split the beam, and this is a compensator. So, light goes in this direction, hit this portion, one portion is reflected passing through this compensator, because this ray is passing only one time to this beam splitter, where other beam is passing twice. So, that we described in the last class. I am not going to do this once again here, and then both the ray is collected here. So, that is ray number 1. This is here, it is reflected from this point. So, this is ray number 2, which is reflected and then from this beam splitter, and then again reflected by this mirror M2, and then come back in the same path. In this case also it is happening like that, and at the end of the day these two rays will merge together and come to our eye or the detector. So, this is ray 3, which is transmitted followed by a reflection through M1, and then this is ray 4. Ray 4 is a combination of ray 2 and ray 3. These two rays are traveling same path if the distance between M1 and M2 is same with this from this beam splitter. So, that was the structure. We described this structure in the earlier, we have already discussed this structure in detail in the last class. I am not going to do that. So, that is the basic structure. So, today what we do, we try to understand that what is the equivalent setup. So, what actually how these things works, that we try to understand. So, from this figure we can see that somebody who is sitting here and looking what is the interference of these two light, it can see the two light that is coming from M1 and M2, because one ray is coming directly from M2, it is coming here, and another is reflected by this beam splitter and coming here, and they will going to interfere through this this ray 4, and we can see the interference pattern. So, let us draw a equivalent picture to make life easy, and the equivalent picture. So, here what we do, this is the equivalent optics for the Michelson interferometer. MI stands for Michelson interferometer. So, what is the equivalent optics? So, let me do that here. So, we have an extended source here, suppose, and then two mirror is sitting here, they are parallel to each other. These are the mirror, because from this side, okay, let me draw first and then I will going to explain. So, this is the source point, say O, and then it is emitting the light like this. So, here the ray will reflect and another ray is also reflect from another mirror, these two. Say this is the angle theta, the ray is going here and coming back like this, and here we can place our instrument which is capturing this interference pattern, but virtually one can see, because this mirror will virtually placed like this dotted line. Okay. And if I extend this, so this is one virtual source, this is another virtual source. So, these two are in same line, they are virtual sources, because if we have say mirror 2 here, and in original case the mirror 1 was perpendicular to mirror 2. So, I just rotate this mirror 90 degree and assume that the placement of the mirror is here in the same direction. Then these two mirrors are having the reflection, and the reflection image will be here, it is here in this point. So, it should be S2 source and this will be S1 prime. This, whatever the plane, whatever the objective we have, from here and here, these are the images of that. Now, you can easily we can show that if the separation of these two mirrors is d, then the separation between these two planes, which are the image, will be 2D. Okay. Now, this angle is theta. So, if we say this is the point O2 prime and this is O1 prime, that is the image of this original point O, then we can see that these two virtual source is not in the same point, but there is a path difference between these two, because they are in two different plane. So, this path difference delta p will be simply, if this length is 2D, it is very easy to show it is 2D cos of theta. So, the path difference is simply 2D cos of theta, where the separation between these two mirror M1 and M2 is D, and if this is essentially the equivalent structure. So, let me write here one by one. So, the mirror separation M2 M1 prime is equal to D. Then the image separation, the image separation of the source plane, S is a source plane, which is S1 prime S2 prime, that has to be 2D. So, their separation will be 2D. Now, the optical path difference between these 2 points, as I mentioned, this virtual source point is of O prime and O. I have already mentioned that this is delta p equal to 2D cos theta, and the fringe. So, this is a, if the source has a extended source, and if the if we have a spot, for example, then the fringe pattern will be that one can have is simply concentric circles So, that is the equivalent picture, equivalent optics for the Michelson interferometer that I have already mentioned in the last class or in this class. Now, we need to check in detail the net optical path difference. This is the path difference we have, but if you look carefully in the previous figure, that the beam splitter, okay, so that the lines are removed somehow. So, one can see that in one case the ray is reflected from this front surface, that is the reflection from highest refractive index region to lowest refractive index. In other case, however, it is reflected from the back surface. In that case, the reflection is from lower refractive index to the boundary is like that. In this side is a lower refractive index and this side is a higher refractive index. So, that means this, due to this we need to have an additional path difference, and that will give us the net path difference. So, the net path difference delta will be delta p, which is this path difference 2d cos theta, that is the geometrical path difference we had, plus the path difference due to reflection. And as I mentioned, the relative path difference. So, let me draw that once again, how this relative path difference is there. So, that was the structure of the beam splitter, and in one case the ray is falling here, in one case it is reflecting like this, and in other case it is transmitted and reflected back. So, in one case this 2 arrow line I am just drawing, it is going like this direction, and in other case this 3 arrow is coming and then get reflected from this region and then it goes here. So, in this, so there is a pi, so this is a beam splitter. So, obviously, there is a pi phase difference that we had here. So, if this pi phase difference we consider, then our condition for dark fringe. So, for dark fringe, the condition will be total path difference delta equal to delta p plus delta r, which is equal to 2d cos of theta plus lambda by 2, which is due to this reflection, that will be equal to the m plus half lambda, odd multiple of lambda by 2 in other word. So, from this expression we can simply have for dark ring 2d cos theta d, sorry 2d cos theta is equal to m of lambda, because this lambda by 2 should cancel out, where m can take the value 0, 1, 2, etc. These are the values m can take. Now, for theta equal to 0, theta equal to 0 means we are talking about central spot, we are talking about the central spot because the fringe pattern will be something like this. Let me draw concentric circles. and this is our central spot. So, for central spot we simply have 2d is equal to m lambda. So, for a given lambda, for a given lambda and d, usually this m value should be very large. So, for central dark spot, or fringe, m, I write max because this is a very high number, will be 2d divided by lambda. Now, for other case, if I go from this spot to other spot, other dark ring, then there will be a value of cos theta. Cos theta will not be 0, and in that case what happened, that d and lambda is same and we have a cos theta value. So, whatever the m value we have for the next ring, it should be less than whatever we have here. So, m max, that is why I write m max is 2d divided by lambda. Well, with this condition, let me now go back to the ring structure and try to understand. So, this is the fringe pattern we have. So, let me draw it. So, this is the central spot, and then we have rings like this. And so on. Now, this is a central spot. So, for central spot, say m max, say this is 100, and then what happened, that if I go to next ring, it will be some less value, and this less value I can calculate, like this is the next lowest integer of m, something like that. So, let me write down the condition first. So, we have for dark ring, we have 2d cos theta is equal to m of lambda, right, and we also have 2d is equal to m max into lambda. So, from these two expression one can get something like 2d 1 minus cos theta, subtracting the lower one to the upper one, then that is equal to m max minus m lambda, or simply p lambda, where p is a new integer. So, p is now a new integer. So, now if go back to this picture, so suppose I have the central one, in this central one the value of m max is 100. If I go to the next one, so my m max, my m value rather will be 99, where I have a p value which is 1. So, that I can have, because here in this equation you can see that my m max will be m plus p. So, m plus p will always be 100, and if I go one by one to the outer rings, the m value will reduce and p value will going to increase. So, that if I add these two, we are going to get back m max. In a similar way, this, for example, this ring, my m will be say 98 and p will be 2 and so on. For third ring, my m will be 97 and p will be 3 and so on. So, another thing, as d varies, now that is important, as d varies, so the fringe, what happened, suppose these two mirror, whatever the mirror we have arrangement, we change the relative difference between these two mirrors. That means, now d varies. So, as d varies, the fringes appear to move towards the center. Where they disappear. Or else move outward from the center. Where seems there, where seems it is originated. So, what is the meaning of that? Suppose I change the relative separation between these two mirrors. So, I have a mirror here. So, this is my beam splitter. Light is falling here, going up. This is the location of one mirror, M2, and this is M1. This is a source point, light is coming here, it hits back going this side and then again coming back, it goes here and then again coming back, both the ray will merge together and come. So, that is the structure. Now, if I the relative separation, the equivalent picture, the M1 and M2 were sitting like this, where this separation was D. This is M1 prime and M2, that was the equivalent picture. This is the equivalent picture, and this is the Michelson interferometer setup, original setup. if I change the separation between M1 and M2, so D will going to change, and when there D will change, the path difference will going to change, and we had the formula in our hand that 2D cos theta is equal to m lambda. So, this order of the, because we are changing D for a particular theta and lambda, m has to change. So, that is why it seems that sometimes the when we do the experiment by hand, we will see that there will be a collapse of these fringes, or it is evolving from the central part. So, if I now just concentrate on the central beam, then what happened? We have for central spot, what we had is 2D is equal to m lambda. Now, I am changing the D. So, if I change the D, what happened? M has to change simultaneously to to maintain this equation, to satisfy this equation. So, simply we can have that delta m will be simply equals to 2 of delta D divided by lambda. Simply we have, so that means if I calculate delta m is what? The number of fringe collapse, and delta D is the change in mirror relative location. So, if that is the case, then we can have m delta m equal to 2 delta D lambda, and if somebody during the experiment, if somebody measure this delta D and delta m, then one can find out what should be the lambda. So, lambda should be 2 of delta D divided by delta m. So, that is an important outcome of this Michelson interferometer setup, that using this one can calculate the wavelength of a given light. So, during the experiment we do this, that a source is here and it is emitting some light with unknown wavelength, and using this setup, using this Michelson interferometer setup, by just changing the relative path difference between these virtual sources, we can find out that how these two light will going to interfere, forming a pattern, and then gradually change the relative location of the mirror. And in order to avail the same condition, the fringes will be, for example, in the central fringes will be somewhere it is collapsed. So, if I find out the number of collapse with the change of this relative distance of m1 and m2, we can calculate through this simple formula, we can calculate the unknown wavelength. So, this is one of the important aspects of Michelson interferometer, and today we discuss in detail. So, we do not have much time to discuss more about this. So, today what we do, we discuss the basic setup of Michelson interferometer, and then we study that how a equivalent optics can be generated through this setup. Through this equivalent optics, we can find out what are the path difference for this kind of setup, and if we know this path difference, then we can calculate that what is the condition for central maxima or central minima. In this case, we find that in the central we always have a minima, always have a dark spot, and by collapsing, by looking the collapsing of the beam, we can find out that what should be the wavelength of the light that is used in this experiment. So, with that note I would like to conclude here. Thank you very much for your attention and see you in the next class.